Thank you very much for the invitation. And my talk, in some sense, is elementary because I will work inside a polynomial ring. And of course, this is a graded ring. And if we choose a homogeneous polynomial, of course, you can define a projective hypersurface. And the corresponding projective space. And we can look also at the complement. And the geometry of this hypersurface is very much related with some algebraic object, which is a Jacobian ideal. Of F. And this is just, it will be denoted by J. And this is just the ideal spanned by the partial derivatives in S, where Fj partial derivative with respect to xj, and this is a homogeneous ideal. Okay, and of course, for instance, y is smooth if and only if the dimension of this quotient as a vector space is finite. So we can check some geometrical properties by looking at this quotient. And the first deep relation between this quotient ring and the geometry of the hypersurface Y is a theorem due to Griffiths. Which says the following thing: if Y is smooth, then for any integer p, we have the following isomorphism of vector spaces. If I take some homogeneous component, more precisely this homogeneous component, this is isomorphic to the P graded piece with respect to the Hoche filtration on the top cohomology of the complement. And here Q is n minus P. And in fact, Griffith's theorem was not stated like that, because this was a little bit before Pierre Deligny introduced the Miss-Hodge structure on the cohomology of non-projective varieties. But Griffith stated it in the following way: if you take the residue here, this residue gives you an isomorphism of this with this PQ cohomology space in the primitive cohomology of the smooth hypersurface P minus 1. One should be or less. Okay, and so as an example, if we assume that p is equal to n, and the degree is not very small, so if we assume this, then we can take some homogeneous polynomial h in this quotient, and consider the following differential form. Which is an element in this in the top graded piece, and then the residue will give us something in holomorphic form on the hypersurface. And here the differential form omega n is the form well known by everybody. Okay, so Griffith's theorem has the importance of doing this, of making these graded pieces in some sense extremely concrete, and this played an important role in Torelli theorems for hypersurfaces and in many other questions. Okay, so now behind this theorem there is a key algebra effect. Related to the Kossuth complex of the sequence of partial derivatives in S. And what is this Kossuth complex? We can write it in the following way. And here omega j are just the global sections on Cn plus 1 of the sheaf of regular algebraic differential forms. So they are just differential forms with polynomial coefficients. Okay, and they I take everything, and I do not shift it. I just keep it like that. And it's also, each of these is a graded S module because I put the weights of the variable and the weights of the differentials to be equal to 1. Okay? And so the key algebra effect is that if y is smooth, then this implies the partial derivatives form a regular sequence. This is sometimes called Macaulay theorem. Right? And so if I look at this complex, all the cohomology groups will vanish except the last one. And the last one, of course, is up to a shift just as a quotient. And so if I want to look at the S homogeneous piece here, this corresponds to S minus n minus 1 here, because a homogeneous polynomial here should be mapped to this product, or omega, not omega n, but just dx0. And so this explains, for instance, why we have this this difference here. Okay, and this fact has also computational consequences, and the computational consequences are that we can compute the Hodge numbers of a smooth hypersurface using a very simple formula. Namely, we have a formula for this Hilbert polynomial. So if I make the sum over all k of the dimensions of the homogeneous components, what I get is and in particular, you see that such a component is non-zero if and only if k is smaller or equal to the degree of this polynomial, and the degree of this polynomial is just this expression. Okay? And so we have computational consequences, and of course a lot of other interesting consequences. Now one can say the result is beautiful, but why we have only some homogeneous components entering the picture? What about the other homogeneous components? Do they play a role in the geometry of our situation? And the answer is yes. And in order to see the other homogeneous components, we have to consider the Milnor fiber. The Milnor fiber associated to F. This is to the polynomial, and this is a smooth affine hypersurface in Cn plus 1. And this is the analog of the local Milnor fiber introduced by Milnor for a local hypersurface singularity. And in this case, it comes with a monodromy operator. Because there is a natural S1 bundle associated to this picture, and the monodromy of this bundle over S1. And the monodromy of this bundle is just given by a very simple formula in our situation. You're just multiplying by some d root of unity. And so there is a morphism at the cohomology level. And moreover, the fact that the monodromy operator has such an algebraic formula tells me that at the level of cohomology, this morphism will respect the Mixo structure which exists on the cohomology of the Milnor fiber. And the relation between the Milnor fiber and the complement is very simple. So this is just default covering. And more in terms of cohomology, the cohomology of U is just the fixed part of the cohomology of the Milnor fiber under the monodromy action. And so for the eigenvalue 1, we have a very nice description. And it is easy to see that the eigenvalues of this monodromies are just because the d power of this map is the identity. Okay. Yes, 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 it's a cyclic cover. It's a cyclic cover. Yeah. But it has a presentation as a smooth hypersurface, and that's why I make it more interesting than other cyclic coverings. Okay, so the relation between this geometrical situation and the homogeneous components of the Jacobian quotient was established by Steenbrink. And his motivation was he was looking for a formula for the intersection, for the signature of the intersection form, which exists on this, on the top cohomology of the Milnor fiber. And he uses a relation between signature and Hodge numbers, and that's why he was interested in establishing such a result. And so again, so if Y is smooth, which is the same as saying that F has an isolated singularity at the origin. Then we have natural identification. If we consider the quotient in degree k minus n minus 1, this corresponds to so this means integral part. That is the largest integer, which is lower or equal to what is inside here. And so this completes the description of the geometrical meaning of these quotients in the case on Y is smooth. And here what it happens is that the only interesting cohomology is the cohomology of dimension n. All the others are trivial due to Milnor result that for an isolated singularity, the Milnor fiber has a homotopy type of a bouquet of spheres. And here we have, if we look at the Mixel structure here, we have a direct sum decomposition. And this will have weight n plus 1. This will have a weight n. All this is part of Steenbrink result. And so, in fact, these formulas combined with the formula for the Hilbert polynomial give us a way to compute all the Hoche numbers in this situation. So again, we have some numerical consequences. Okay. Great. So now what I plan to tell you today is what happens when Y has isolated singularities. So why isolated? Because this case is already difficult. I would like to tell you in general what happens, but already this case is quite difficult. So now assume that A is such a singularity. Assume that we have a local equation and so this G will be a function of some local coordinates y1, yn, and then I will define two numbers. The first number is a Turinan number, and this is the dimension of the local ring of Pn A divided by the ideal spanned by all the partial derivative of G and G itself. And another number which will play an important role is the number which was defined in the previous talk, is a log canonical threshold, which is actually the log canonical threshold of the pair formed by P, Pn and Y at the point A. And I won't repeat the definition, but I'll give you an example. If the local equation has a very simple form, is a polynomial of Briscorn Pham type, so assume that local equation of the singularity is like that, then the corresponding log canonical threshold is just the sum of the inverses. And in my talk, a node, pardon? Ah, okay. Then then I will call this Arnold singularity index. Okay, I define an invariant which is sometimes a log canonical threshold if it's bigger than 1, and otherwise I will call it Arnold index. And actually, Janos Kolar established the exact relations between the two numbers in his paper, Singularity of Pairs. I refer to this paper for an exact. Pardon? It was given in the talk using log resolution. One can define it. Okay, so a node is, in my talk, nodes will appear which are the simplest singularities. They are called A1. And in this case, all of these integers are equal to 2. And so you see that this invariant LCT over node, it's equal to n over 2. Okay, and there are various other interpretations. For instance, for an isolated hypersurface singularities, there is a notion of a spectrum which describes the interrelation between the semi-simple part of the monodromy and the Miswa structure on the cohomology. And this invariant is the smallest spectral number. Okay, and using this definition, it is easy to show that if we are in dimension n, then for any singularity, this invariant is at most n over 2 and is equal to n over 2 if and only if it is a node. And for us, so the nodes have the highest possible invariant. This will be the interesting part. And I will define alpha of y to be the minimum of all these invariants for A in the singular set. So there are finitely many singularities, so I will take the minimum, and so I get a positive rational number. Okay. Now, it's time to state a result, I guess. So I will state now generalization of the theorem due to Steenbrink in the case of hypersurfaces with isolated singularities. Okay, and so it is not completely satisfactory. You will see. So this is a result due to Morihiko Saito. And myself. And it says the following. It says that theorem 2 holds for a hypersurface with isolated singularities for all k.
So it's theorem 2, Steenbrink's theorem?
Yes. We can put a number. Yeah. Yeah. Thank you. Thank you very much. It was in my notes, but somehow I decided I don't need two, and here I need it. Yeah. So this is for all k satisfying k over d at most alpha of y. Okay, so you see that if I look, if I compare here, essentially this condition says nothing because beyond for larger k I get 0 on both sides, so this is just to give you an idea what is the range where this equality says something interesting. And if we compare this with the bound over there, in the case of nodal hypersurfaces, you see that we go up to half of the dimension. So up to half, the first half, we have a complete understanding of what is going on. And actually, a special case which corresponds to theorem 1, the theorem by Griffiths. Theorem 1 holds for Q, and this appear in a paper by Saito, Lawrence Waslow, and myself in 2009. And actually this special case plays a key role in the proof of theorem A, because in some sense we can reduce the general case to the special case by replacing A, F with some function obtained by adding a new variable, the so-called Thom-Sebastiani construction. And so maybe we need several new variables here, but the idea is that the eigenvalue different from 1 for the monodromy here becomes an eigenvalue equal to 1 in such a suspension. Okay, so now we can ask what can we do for the other values of k. We have seen that up to the middle we have some result. What about the rest? And now we have some partial results, nearly complete, only for nodal hypersurfaces. And I will yes? Yes. In this case, the Hoche filtration is somehow described, but the wave filtration is quite complicated. We do not have such a result. And I have looked a little bit at hyperplane arrangements, and even there is not at all clear. In the case of a hyperplane arrangement, this part is very well understood and has a Tate-type Hoche structure, but this part is quite mysterious, even for hyperplane complements, even for well, for lines in P2, I can tell you practically everything, but if you have planes in P3, it's already complicated, and I cannot Okay. So in order to describe the result for the other values of k, I need some definition. So we define a sequence of homogeneous ideal which are denoted by IL inside S. And because they are homogeneous, it is enough to describe the homogeneous component for each T. And the homogeneous component for T is like that. I look at homogeneous polynomials of degree T in S. And I look what happens when I take the germ of such a polynomial as a singular set. So sigma is a singular set of Y. And here I take the local rings of the projective space divided by the L's power of the maximal ideal.
So this T is not that T over there.
Now.
It's just a
Yes. Yeah. Maybe it was bad. Too many M's. Yeah, that's the problem. That's the problem. Q was already used, so B. B the best. Okay. And so, by definition, the B's homogeneous component of this ideal is the kernel of this map. That means all the homogeneous components of degree B whose L jets vanish at the singularities of our hypersurface. So if L is equal to 1, so I1 is just the radical of the Jacobian ideal, that is all the polynomial vanishing where on the 0 set of the Jacobian ideal. But already I2, I3 is quite complicated because I2 clearly contains the product, but it's not at all clear that they are equal. Okay, so using this notation, we can state theorem B. So assume, so when I in this discussion, I assume already Y nodal, so assume Y is nodal, hypersurface. That is has only A1 singularities. Then one had the following. The piece, graded piece of the top cohomology of the complement with respect to the Hodge filtration is given as follows. Okay, so the graded pieces are quotients of this sequence of ideals, and we should take some homogeneous components. The m here is just the integral part of n over 2, which is alpha y in this situation. And now we have to add some extra conditions. And either this means that if one of these is satisfied, then the above formula is okay. For instance, if n is even, everything works fine, so there are no more conditions to add. The second is that n is odd, and so if n is odd, we have a gap between m and m plus d over 2, where we cannot conclude. So outside this gap, we can prove that the formula works fine. But we have this gap, and there we cannot conclude. And this gap can be avoided. This gap can be avoided. So I will write here n odd and any q if the number of nodes not too big. And I will give an example of a result of this type. So a result due to Chertsov implies that if the number of singularities is bounded by d minus 1 square, and if d is at least 7, then the formulas work for any q. And we have various versions. Some of them work for n equals 3, some of them for n equals 5, and starting with d, some of them work for d equal sorry, here is n. Some of them work for n equals 3, some of them for n equals 5, and for n equals 7, this is the best the best result we have. Okay. 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 Mm-hmm. So we fix an integer b. we fix an, so I will define a sequence of homogeneous ideal, EL, right? And all of them are homogeneous ideals, so it's enough to define for each B, for each integer B, the B homogeneous part. And so I take the homogeneous polynomial of degree B, and I evaluate such a polynomial at each of the singularities. And there I check if all the L jets are trivial. That is, if they are if sorry, Thank you very much. It is a big mistake in the statement. Thank you very much. The Jacobian idea should be present here. Thank you very much. Thank you very much. So in this formula, I have this sequence of ideals and also the Jacobian ideal. Okay, good. So now I will like to discuss some unexpected, at least for me, consequences of these results. We have seen already that if y is smooth, then the partial derivatives form a regular sequence, and being a regular sequence, this means essentially that if I look at the previous cohomology group, so this is equivalent to say that the previous cohomology group is trivial, and this means that any relations which I may write, so if I write a relation of degree S, where all the coefficients aj are polynomials of degree S, then this relation is necessarily trivial. That is, comes from some Cauchy relations. So these Cauchy relations span an S submodule in the space, in the module of all relations, and in the case of a regular sequence, all relations are of this type. Okay, and this is actually equivalent, and so as soon as we have isolated singularities, there will appear some interesting relations. By interesting, I mean they are not consequences of Cauchy relations, right? And the question is, what can we say about these relations? Should they appear in low degrees? Should they appear in large degree? And I will give you an example, and then I will state the result. For instance, if you look at the plane curve given by this equation, then you have clearly some relation. I will denote by fx the partial derivative with respect to x. So this is a relation which is non-trivial because cannot come from from a Cauchy relation. The Cauchy relations start to appear with coefficients in degree d minus 1. Okay? And the surprising result is the following here. So assume Y has isolated weighted homogeneous singularities. What does it mean, weighted homogeneous? Instead of writing a long definition, I will write a characterization given by Kyoji Saito, which says that an isolated hypersurface singularity is weighted homogeneous if and only if the local equation belongs to the Jacobian ideal spanned by the partial derivatives of G. And so we assume that Y has isolated weighted homogeneous singularities. And then the conclusion is that then any CCG Rs of degree S, which is bounded by alpha y times d minus n, is trivial. Of the coefficients, And so you see that, for instance, if we are in the case of a nodal hypersurface, here we have n over 2, and I will discuss a special case to see that this result is sharp. So assume that y is in P2, a nodal curve. So in this case, alpha y d minus n, this becomes d minus 2. And so this is trivial for S strictly smaller than d minus 2. This is a consequence of this theorem. And maybe in this classical case, the result was already known. I think so. But now if I look at the dimension of the relations of degree d minus 2, this is exactly the number of irreducible components of C minus 1. And you see that for d minus 2, we can get non-trivial relations. And I can write you explicitly how you get such a relation when we have two. C is, sorry. sorry. I can write you an explicit relation when we have just two irreducible components. So when F is has a factorization like that, then there is a non-trivial relation coming from the following fact. So a non-trivial relation comes from finding here a two-form such that the wedge product with df is 0. And it's enough to take the two-form given by the wedge of the differential of the two factors, and this gives you a non-trivial relation. And in a paper with Gabriel Sticlaro we explain how to write a basis for this vector space in the case when there are several irreducible components. And in such a case, it's not necessary to take such simple formulas. You need to modify them to get really relations. But what is a little bit strange here is this extra condition. And now I will explain a little bit the whole strategy of proof for this result and why such a condition appears. And on the other hand, I can tell you that I have weaker relations without this hypothesis, but I'm sure that someone clever enough will be able to prove this result without this assumption. But our methods do not allow us to do this. So I'll briefly tell you how to prove such result. There are just a couple of minutes left, unfortunately. So if we look at the cohomology of U, actually all the cohomology group of U, here we have two filtrations. We have the Hodge filtration and we have the Pole order filtration. And these two filtrations are related. One has such an inclusion for NES, and this is a result which Pierre Deligny showed me 25 years ago. So, and shortly after the paper, Morihiko Saito showed that in fact one has equality in some ranges. So the ranges is so if we are on the J's cohomology, then this S should be. And so in some ranges which depends on this invariant, we have equality between these two filtrations. And because of that, we can use the pole order filtration in order to compute Hodge filtrations. And now the pole order filtration comes from a filtration on a complex of rational differential forms. Such a filtration has an associated spectral sequence. And the spectral sequence is an E1 spectral sequence where there are two parallel lines of non-trivial terms, and it's unbounded is not a first quadrant spectral sequence, and we have here some differentials, D1. And in the case of nodal hypersurfaces, we can show that this spectral sequence degenerates at E2. And for weighted homogeneous singularities, the spectral sequence behaves as if it degenerates at E2. We believe it degenerates at E2, but we are not able to prove. But for singularities which are not weighted homogeneous, we can prove that it does not degenerate at E2. And because of that, the control of non-weighted homogeneous singularities is much more complicated. Okay, so I guess I will stop here, and thank you very much for your attention.